Let's admit all. Let's admit all. Let's admit all.
Maybe we can unmute the YouTube.
Let's admit all.
You can unmute the YouTube. You can unmute the YouTube.
Yes, I'm working on it.
Okay, so while people are joining, I would like to ask everyone to make sure that your microphone is muted so we don't have this looping from Zoom or any background noise. We will start in one or 2 minutes. I see that people are still joining, so we will start in a few minutes. Okay, maybe I think we can get started now. Hello, everyone. I hope you are having a great time wherever you are. My name is Sajjad Tadashisila from Carnegie Mellon University. On behalf of my friends, Sushil, Greg, Francesca, Julia, Mike, and all the MATLAB group members, I would like to welcome you to the final session of the MATLAB webinar series. We started these webinars in early May and are extremely excited to have hosted about 10 webinars so far. And we are equally excited to have 2 spectacular scientists who have had tremendous impact in advancing the field of polymer science, but also training new generations of scientists and researchers. So it's our great pleasure to welcome Professor Craig Hawker from the University of California, Santa Barbara, and also Professor Krzysztof Matyjaszewski from Carnegie Mellon University. The general theme of today's talks will be on controlled polymerization and also controlling the structure of polymers for different applications. So I think it would be really a great source of education, but also inspiration for all of us. So as Chris will be a guest today, I wanted to take the honor of presenting our speakers. But before that, please let me mention again that you can use the chat panel in the Zoom, or for the people who are watching us on YouTube, you can use the live chat panel to comment, to ask your questions, or write anything about yourself, and we will read the questions to our speakers at the end of their talks. Also, Craig and Chris kindly agreed that we can continue the discussion at the end of the meeting to discuss about some other general topics that we face in academia and especially in polymer science. So please feel free to ask your questions at the end that are not specifically related to what they will be presenting in their talks. And we have also people joining us on YouTube. So I would like to welcome you all in Zoom and also on YouTube. So maybe I can start by presenting Professor Craig Hawker. Professor Hawker is Clark Professor and holds the Allen and Ruth Eager Chair of Interdisciplinary Science at the University of California, Santa Barbara. He's the director of the California Nanosystems Institute, the Materials Institute, and the Materials Research Lab at UCSB. He became a research staff member at IBM Almada Research Center before joining UCSB in 2004. His research is focused on synthetic polymer chemistry and nanotechnology, integrating fundamental studies with the development of nanostructured materials for various applications from microelectronics to healthcare. He has been recognized as a fellow of the Royal Society, American Chemical Society, and the ACS Poly and PMZ divisions, and also a fellow of American Association for the Advancement of Science and a fellow of National Academy of Inventors. He has received numerous prestigious awards, such as ACS Award in Polymer Chemistry, Centenary Prize by the Royal Society of Chemistry, Arthur Cope Scholar, and many other awards. But also he is an editor of Journal of Polymer Science, which I think we will all agree is the best polymer journal ever.
Yes, well done.
Exactly. So with that, please join me in welcoming Professor Hawker to present his talk.
Great. Thank you for the introduction.
So Francesca, if you can stop sharing. Oh, perfect.
Okay. Well, thank you, Chris and his group, for the introduction and the invitation to speak to you today. I'm going to tell you two stories that really encompass what I've tried to do in my group over the last 20 to 30 years, and that's develop control polymerization processes. And I'm going to show you today what I like about this area in terms of the beauty and the benefits, to show you why you would go to the small effort to prepare controlled materials. And a lot of this work is motivated by this quote from Sir John Cornforth, who won the Nobel Prize in 1975. And you can read the quote right here. In essence, it's telling us to make chemistry simpler. If we can make chemistry simpler, more people will use it. We'll get materials into a much wider array of researchers' hands. And in effect, it's going to be really the best for the advancement of the field. And so this is a quote that I've really taken to heart over the last couple of years and have worked with my group to really develop controlled polymerizations that are easy to do. And if we look at controlled radical polymerizations, we can see that Sir John Cornforth's thoughts really come into play. The polymerizations are easy, they're getting easier, and that's what I'm going to concentrate a little bit on today. They're versatile, and they're getting more versatile, again, something I will concentrate on today. And they are proving to be extremely powerful in many applications. And so in terms of enabling chemistry, I would say that controlled radical polymerizations and controlled ring opening polymerizations are two examples of enabling chemistry. And if we look at controlled radical polymerizations, we can see that there are two real pioneers in this field. And I'd like to take a second to really acknowledge all the work that Chris Matyjaszewski and Mitsuo Sawamoto have done in this general area and in the genesis of this area. Many people on the Zoom call today were probably not alive when I used to sit during the seminars of Chris and Mitsuo back in the early 90s when they were first developing atom transfer polymerization. It has, I think, expanded and been much more successful than they could have envisaged at the time. And it's really become a staple of nearly every research lab around the world. I teach it in my class. I'm sure that it's taught in nearly every polymer science class in the world, which is unbelievable for a chemistry that is only 25 to 30 years old. And I'm really actually very happy that Mitsuo and Chris are starting to get a wealth of awards in recognition of this. And I really do think that there are even greater awards coming for Chris and Mitsuo in the future. One thing I'd like to go off on a little tangent now and tell you about these two covers for the Journal of Polymer Science and the Journal of Polymer Chemistry. Both of these are actually paintings, and they were paintings done by a very famous Dutch artist. And that artist is actually Letty Meyer, who is the wife of Bert Meyer. And so I think this really demonstrates one thing that's very important today, and that's community. And I really do like the community that has developed in the polymer synthesis field, the polymer science field over the last 25 to 30 years. It was certainly something that attracted me to the field, and I'm glad, and we see the number of people who are Zooming in today, the contributions back from the Matyjaszewski group. It really shows that there's a strong community. And in times of COVID-19, this type of community is actually really important. So let me just give you one more thing that I like to point out about Chris. Actually, two things. First off, I have an array of photographs, as you can see, of Chris at various times in his career. The thing that I always notice when I look at these photos is he has not aged at all. And so for those of you that may be aware of a book called The Picture of Dorian Gray, I am sure that there's a painting of Chris that's aging really badly in his attic, and Chris in real life is not aging. The other thing that I want to point out, and I checked this yesterday, and that's Chris's H index is 188. Let me put that in context. If your H index is approximately your own age, that's actually really good. That's a very, very successful H index. If your H index is double your age, that's fairly off the charts. However, if your H index is about triple your age, you're in a select group of 2 or 3 researchers worldwide. And so again, I think this demonstrates the impact that controlled radical polymerizations have had, but also the impact of what I started at the beginning talking about. And that's the community is really looking for easy chemistry that gives you well-defined materials. And so ATRP has really exploded based on these principles. We can now make as wide a composition of materials as we could before with other structures that we couldn't make using, for example, living ionic polymerization. And the two enabling features are that the catalysts and the initiators typically tend to be commercially available or very easy to prepare. And as I will show you, they're very simple to run polymerizations. So I always like to say that a physicist can now do polymer chemistry and make low polydispersity materials. And with ATRP, they certainly can. So our group's entry into the world of ATRP was fairly late. About 6 or 7 years ago, I had a wonderful postdoc from MIT, Brett Fors, who's now a professor at Cornell University. And Brett came into the group wanting to do something in the area of ATRP. But again, we wanted to do it in such a way that it would either push the field in a different direction or make the chemistry easier. And so Brett developed, using a set of iridium catalysts, a photo ATRP process that really proved to be very simple and gave us a switch that we could easily turn the polymerization on and off. And one of my most recent papers is a joint paper with Chris and his group looking into what happens during the dark time during this on-off process. The other person that has really driven ATRP in my group is Athena. She was a Marie Curie fellow at UCSB for a number of years from Dave Hamilton's group at Warwick. Athena is now a professor at ETH. And I'll show you in a second that Athena really pushed us to develop simple chemistry that goes to very high conversion. So we're going to use a lot of Athena's chemistry and also the inspiration from Brett in the things I'm going to talk to you about. And the two areas, I'm going to start by showing you some of our work using controlled polymerizations to make novel discrete oligomers, and then make them on a synthetically viable stage by combining controlled radical polymerization with automated chromatography. The second area that I'm going to talk to you about is how we use this combination of controlled synthesis, automated purification to very easily make block copolymer libraries. And from those libraries, we can observe some new nanoscale morphologies that a number of them were predicted not to be stable, but synthetically we have been able to prepare them and demonstrate that they are stable. And just a little plug to Amazon, which I think is now worth over $1 trillion, so they don't need any free advertising. But I just wanted to put this in because this is the reaction vessel that I always order from Amazon for the group. It's a commercial UV nail dryer, and they're $30 from Amazon, and we have quite a few in the lab, and they allow you to really do these polymerizations very readily. So if we go back to the first area, and that's the discrete oligomers, this work was inspired by Dave Terrell, who's down at Caltech, and after dinner talk he gave maybe 10 or 12 years ago at an ACS meeting. The thing that Dave said that really stuck with me was when you look at these samples of polymethyl methacrylate or polystyrene, they're dispersed polymers. And in actual fact, if you do the statistics, no two polymer molecules in these samples are the same, which is a really interesting thought when you think about it, that for macroscopic objects, no two polymer chains are the same in that sample. And this is different to nature. Nature, when they're trying to store information, will often use discrete molecules, molecules that have a dispersity of 1.0. Even in the best controlled polymerizations that we have out there, we're going to get a dispersed mixture, typically dispersity of 1.1 to 1.2. If we do it really well, could be 1.05. So there is a dramatic difference between how nature uses some of its building blocks and what we're limited to. And so the question naturally arose is, why do we want dispersity to be as low as possible. What properties does that allow us to address that we couldn't before? And what advantages do discrete materials bring? This, in recent years, has actually been further pushed to not only ask the question about discrete materials, but for synthetic polymers, sequence defined materials. And I think sequence defined materials is really a major area for the future. But if we go back to dispersity, we see some beginnings of the advantages of dispersity. And I'm not going to go into this in great detail, but there's these two papers by Bert Meyer and Larry Sitter showing that when you do have discrete synthetic chains in molecules, such as I'm showing you here, you do get novel properties. And in these two cases, it really impacts the morphology and the nanoscale assembly of these materials. So dispersity may play a key role, but in both of these cases, it was really difficult to synthesize these materials and actually quite laborious. And you can also see this in some work that Kenichi Takezawa, who was a visiting researcher from Mitsubishi Chemical, did in my group a number of years ago. And Kenichi took on the multi-month task, and seriously, this work is probably about 6 to 9 months work, of making a library of oligocaprolactones. He made it up to a 128 mer. Unfortunately, that becomes too small to show on the screen, so I'm just going to show you this 64 mer. But he went through and in a stepwise fashion made this 64 mer oligocaprolactone, which we were able to show had 64 repeat units, not 63, not 65. His chemistry allowed him to make exactly 64, had a discrete molecular formula and molecular weight. The problem was that the overall synthesis of this material was 18 steps with an overall yield of about 1.3%. And so Kenichi was a really hard worker, but it still took him about 6 to 9 months to make a couple of 100 milligrams. And so that was great. We actually learned a lot about the crystalline behavior and the crystal structure of caprolactone from this work, but it still was much more synthesis than we would have liked. If we look at how Kenichi did this work, he started with the monomer, made the dimer, then did protection, deprotection chemistry to couple two dimers to give a tetramer, protection, deprotection chemistry, coupling to give the octamer, so on and so forth. So it really is a stepwise process. It's hard to get odd numbered materials. It's also hard just to make materials, as I say, time consuming and low yields. So around about this time, we were starting to think about easier ways to purify polymers. And so the question naturally arises, is there an easier way to make oligomers? And can we take advantage of controlled polymerizations? Because if you remember, controlled polymerizations allow us to control molecular weight, and they give us low polydispersity materials. And so Will Guttenkust, who was a postdoc in the group and is now down at Georgia Tech, and Jimmy Lawrence, also a postdoc in the group, who's now down at LSU, took this project on and came up with what I think is a really smart approach. They let the synthesis do a lot of the work for them in terms of controlling molecular weight, getting relatively low polydispersity, but being able to make large quantities of materials. And they coupled that with purification using an automated chromatography system. So in essence, it's easy to put on an ATRP reaction to make 30 grams of materials. It's about a 1 to 2 hour process. And as you can see here in this graphical representation, that's going to give you a set of oligomers. But you can then use chromatography, again, a couple of hours work, to hopefully, if you do the conditions correctly, take that oligomeric material and separate it into discrete hexamer, heptamer, octamer, and so on. And so that was the general strategy. Alison and Jimmy put it into effect. And the first example that they chose was, as you could expect, atom transfer radical polymerization. Chemistry that Chris and his group have defined over the years. We're going to polymerize tertiary-butyl acrylate using a commercially available initiator, but we're going to run it to a relatively low degree of polymerization. We still get dispersity, but then we're going to take this dispersed material with around about the molecular weight we want, and then pass it through one of these commercial automated chromatography systems. We use the system from Biotage. They have never given us any freebies, even though I've advertised them worldwide. But it is a simple technique and a simple system to use. And so the idea is very simple. You take that polydispersed mixture and you flow it through your column with the right elution characteristics and elution solvent, and you start collecting fractions. And as I'm showing you here graphically, we have fractions that are pure tetramer, then we transition to a few mixed fractions, and then pure pentamer fractions, mixed fractions, and then pure hexamer fractions. So we have stepwise elution of the oligomers, and the job is to collect each fraction, analyze the fractions, and then decide which fractions to combine. I should point out that because we want this to be simple, we're using standard columns and standard conditions. The only challenge in this work is working out the best elution solvent or elution gradient to use. And with that, you can actually make materials that are either difficult, if not impossible, to make using standard techniques. These are just the MALDI mass specs for the pentamer, the hexamer, the septamer, octamer.
We do not hear you. No, still there is no voice coming from you. No, yeah, it's still not working. Can you like unplug and try with the laptop's microphone? Possible? No, it's still nothing connecting, but we can't hear you. No. Okay, I think we can hear you now. Oh, no. Is it possible to use the computer microphone? Okay, would it be possible to reset and join again, to stop sharing and share again? Okay, no. Fortunately not. If it is possible, you can use your phone to connect to the meeting. Let's find the, Sushil, can you share the number that he can call in?
Yes, let me do it.
So I just send the number that you can use to dial in. Should be. So there is a comment on Zoom that you can change settings from Zoom, I believe. You should go to sound settings, sound control panel, go to microphone tab and disable undesirable mic and enable the desired mic that by right clicking. I can even share this with you.
Hello.
Hello there, hello. Okay, we can hear you now.
Good. Let me just try and resurrect everything. Okay, can you hear the screen? See the screen now?
We can see only you.
Okay.
As you can share the screen.
Okay, I'm trying to re-enter. Can you send me the Zoom invitation again?
You are in Zoom. If you go to the Zoom window, you can go to share a screen button at the bottom of the screen. It is in green color.
Yeah, I don't think I'm actually in the meeting anymore. Or maybe I am.
No, you are. We can hear you and also see you from your computer.
Okay, I'm having.
I sent you the link. You can rejoin using that link.
Yeah, just. I'm gonna leave and then try and come back.
Yeah, leave and try again. So in the meantime, that Professor Hofer is joining, we had a question that if the presentations will be available on YouTube, and I should say yes, they will be available for a few, for 1 or even more days. So you can also access them later if you want to know more or miss. So hopefully this time it will work. Okay, we can.
Okay, do we have it back?
Perfect. Yes, you are back.
Good. Well, sorry about that, everyone. My marvelous headphones from my youngest son obviously ran out of juice. But in essence, what I was saying is that we can now prepare and purify these oligomers. Can prepare and isolate these oligomers in synthetically useful amounts. So you can see here, we can now make grams of these materials very easily. And one of the other nice features about this process is that we can actually start to ask questions about, so what can we do with these materials? So I'm just showing you here the crude polymer that we start with. We can then separate that into the trimers, tetramers, which are viscous oils. But then surprisingly for us, these oligoterabutyl acrylates started to become waxy. And so then we looked into more detail in the pentamer. And what Jimmy and Alison were able to do was to re-purify that pentamer. So now we're looking at pure pentamer. The beginning fractions of pentamer, the ending fractions of pentamer, but we do still see a separation. And the initial fractions, as you can see here, are really waxy and, you know, not that much crystallinity to them at all. And the later fractions were very highly crystalline. So what I think that we're doing here, and we're still looking at this, is that we're starting to now actually separate the pentamer according to all of the possible diastereomers. And obviously, the materials that are eluting later in the separation are just a little bit more crystalline because of their tacticity than those early in the separation. So these were some unexpected properties in chemistry that we started to observe for these materials that we were able to separate by biotage. And so the next big question that we had to ask ourselves is, how general is this strategy? Does it only work for low molecular weight acrylates? Can we expand this to other polymer building blocks and backgrounds? And that's going to be basically the rest of the presentation today, how we looked at expanding this to many other systems. And again, this is some work that Jimmy and a visiting researcher from Japan, Eisuke, took on. And again, controlled polymerization is our starting point. In this case, the controlled synthesis of P3HT. We're going to use a dimer strategy. So the crude mixture of this has hexamers in there, octamers, decamers, dodecamers. You can see it's a fairly broad distribution of oligomers, even though the dispersity of the crude polymer is about 1.1, 1.15. But again, we can put some effort into choosing the right solvent to elute this from our biotage columns. And we eventually looked into pentane, which, as you can just see from the TLC plates, does start to separate out the oligomers. This is what the biotage column looks like. It's actually a really pretty separation because of all the colors. But it's even prettier based on what you get out. Here I'm showing you from a 3-gram crude oligomer mixture. Again, we're getting very high retention of the mass. We're also getting samples that have reasonable quantities, all in the hundreds of milligrams from the tetramer all the way up to the dodecamer. And again, you can synthesize the dodecamer using a stepwise strategy, but it's about 12 plus steps and the overall yield is extremely low. Here we're getting it in a single step. And so this was a real, I think, big step forward in the terms of oligomer chemistry. But the beauty about looking at oligopoly 3HT derivatives is that they are conjugated, and their conjugation length really depends on what the degree of polymerization is. So here you're seeing the crude material that we're starting with has an average DP of about 8, and what we separated into the tetramer, hexamer, octamer, decamer, dodecamer. And just visually, you can see that the photoluminescence of all of these are significantly different, and they're significantly different from the crude starting material. The nice thing is that now we have the pure materials, we can go back and make mixtures. And this may sound funny to think about, that you've just taken a dispersed mixture and you've separated into discrete materials and you're going to make a mixture again. But again, we're not making a crude random mixture. We can make mixtures that are precisely tuned to what we want. And so in this case, you can see the color of the crude mixture, the color of the tetramer and of the 12mer. And the interesting thing is that when we do a 1:1 mixture of the tetramer and the dodecamer, we actually get a mixture with an average degree of polymerization of 8, the same as the crude mixture. But because we've really controlled the length of what constitutes that mixture, we now get white emission. And for many of these light emitting applications, you really need white emission if you're going to be able to commercialize these materials. So this was a really nice demonstration that we could expand this concept of controlled radical polymerization and automated chromatography to a wide degree of backbones and also a wide degree of applications. So in the much shorter second section that I'm going to finish off today, I want to expand this to some more recent work that we've done, looking at easier way to make block copolymer libraries, and does that allow us to discover new nanoscale morphologies. And so the big question in this section is, I've shown you that we've been able to purify easily oligomers. DP equals 10, DP equals 12, we can do that. But does this concept of combining a controlled polymerization with automated chromatography allow us to purify high molecular weight polymers? Does it have any advantages in this area? And so for this, we actually have to go back a little bit of time and say something that I am sure Chris will agree with me, and that's the beauty of and power of collaborations in polymer chemistry. So for all of you that can recognize me here, I have aged badly, even unlike Chris. This is only a couple of years ago. But the point is that I joined UCSB knowing very little about polymer morphology, polymer physics, theory, simulation. And it was only through collaborations that I learned a little bit and enough to make me dangerous. So I'm going to tell you about the inspiration, and it was this joint postdoc that Gleb Fredrickson, who has taught me an enormous amount about polymer theory, the late Ed Kramer, who was really inspirational with all of the work that we've done in block copolymers and polymer morphology, and Chongbing Tang, who's now a distinguished professor down at University of South Carolina. We started examining this concept about controlling block copolymer morphology. And in essence, this is what I took from a lot of that work, and it's your fairly classical textbook block copolymer morphology diagram, where you have spheres, the spheres become cylinders. If you're very, very lucky, you may catch the gyroid phase. It's actually quite difficult. You get lamella, and then you get the inverse structures. And that's what people print in textbook. It's what I teach in my class. to me, until very recently, I thought it was all governed by the fraction of each domain and also chi-n, where n is the degree of polymerization and chi is, in essence, how much each domain dislikes each other. And so that's what I thought was polymer morphology and the only things that really govern polymer morphology. But again, it's really good to have young colleagues, and I'm very fortunate to have Morgan Bates and Chris Bates as young colleagues here at UCSB. And they corrected me and told me that I was wrong, and that chi-n and the fraction are not the only things that really dictate morphology. You can actually tune it with other parameters such as conformational asymmetry, basically the thickness of the polymer chains. And if you choose your monomer units correctly, you can really have significant asymmetry between these two chains. And so this is a really another tool to tune morphology. So Morgan, together with Stephanie Barbon, a postdoc in the group who's now at Dow, did what everyone traditionally did, and that's make a library of different block copolymers using classic control radical polymerization. So you'll see the trifluoroethanol, which is this privileged solvent that Athena introduced to the group, works really well for the polymerization of acrylates, and it's a fairly simple thing to make multiple starting acrylate blocks, and then using controlled ring opening polymerization to open lactide to give polylactide, polydodecyl acrylate diblock copolymers. And using these techniques, it was a couple of months of work, but what Morgan and Stephanie were able to do was to make well-defined materials. They had a library of about 15 diblock copolymers, and when you work it out, that's around about 30 polymerizations, 30 purification steps. So it's a bit of a challenge, but they were able to make all of these different materials to start looking at the morphology of these diblock copolymers. And lo and behold, because they had prepared enough samples with enough range, they were able to find this unique A15 phase, which has been predicted to be unstable for diblock copolymers. It's a spherical phase with a very large unit cell. And even I, who do not know that much about Sachs patterns, will recognize how pretty this Sachs pattern is for this A15 phase of this polylactide, polydodecyl acrylate diblock copolymer. The other interesting feature that I found from Morgan and Steph's work was that these materials were stable. You can extend and anneal these for long periods of time. And again, unlike the predictions, the A15 phase proved to be stable. But if you just remember, again, we see the trap. And the trap is that we had to do multiple polymerizations to make this library and then examine the library. And again, you see where this concept of user-friendly chemistry comes in handy. And this is a collaboration with Andrew Whitaker from the University of Queensland in Australia and a joint postdoc, Cheng Zhang, who again took the concept of controlled polymerization, married it with automated chromatographic separation, and takes an AB dye block, one parent sample, and then makes a fractionated library. And the hope is that fractionated library would scan all of the fraction volumes that we could then look at morphology. And so this is in essence what Cheng did using a simple gradient solvent elution profile. And the first thing I want to go through is that in all of the samples that we look at, we tend to find an initial peak, which is one of the homopolymers. So not only do we start to fractionate this material, but we actually make this material much purer than the starting diblock copolymer system. It's really easy to get rid of the starting homopolymers in these samples. So again, you use your solvent gradient and you start collecting multiple fractions as you increase, in this case, the amount of ethyl acetate in hexane. And you see what happens. Here we have our parent diblock copolymer. The fraction of lactide is 34%. And if we look at the elution fractions or time, you can see that we're starting to get diblock copolymers that have very low amounts of lactide. Then as we collect more and more fractions, we increase the amount of lactide until our final fractions are 48% polylactide. Now, one of the important things that we've always focused in this work is it synthetically useful? Do I get much material out? And you can see from this plot that you do get a very good mass recovery. We start with 2.5 grams of the parent block copolymer, and we obtain 2 grams of fractionated block copolymers, as well as the other couple of 100 milligrams tends to turn out to be unwanted homopolymer contamination. And so from one sample, we now have materials with a broad range of levels of lactide incorporation. And if we look at each one of these samples individually, you can kind of get a sense for what is happening. The length of the dodecyl acrylate for all of the samples stays about the same. Maybe it decreases just minimally. But if we look at the relationship between the amount of lactide and the elution volume, you can see that increases fairly consistently. So in essence, it's the polar polylactide block that controls separation. We also see that the smaller copolymers elute first. And the other nice feature is that we start with a material with a polydispersity about 1.1, just a little bit above 1.1. And each one of the eluted samples has very low dispersity, anywhere from 1.05 to about 1.08. So we're not only purifying these materials, we're also fractionating them and giving us a library of materials that we can start to look at. We've characterized these using all the standard techniques, and it really is operating as I've told you. You see the fraction that we obtain at 12 minutes is that contaminant. It's the polydodecyl acrylate homopolymer. It has no lactide in it whatsoever. Then as we start to collect more and more fractions, you see that the amount of lactide increases significantly from the early fractions to the later fractions, directly correlating with the plot that I showed you before. So we now have the ability to make these polylactide polyacrylate libraries. Do we see an effect on the morphology? And do we see that we observe unique new morphologies? So again, this is our starting workhorse. This diblock copolymer has a fraction of PLA of 34%. And as you would expect, and this agrees with literature, it's a parent hex phase. So cylinder phase, exactly what you would expect. Then you go with and examine your fractions. The early fractions are disordered. We then have fractions that are around about 21% that clearly are BCC. And then lo and behold, the new things start to pop up. Now, at approximately 22%, we are starting to see what's called a sigma phase. We then observe the A15 phase, hex, and then lamella. So from this one single parent copolymer using a fairly simple chromatography separation procedure, we're getting a library of materials that we can start to observe a really complete morphology picture. So this is what Stephanie and Morgan were able to do using the conventional method, as I said, 15, 20 polymerizations and associated purification steps. And you can see that we get a reasonable idea of what the phase morphology is like. But remember, there's homopolymer contamination in this sample. The samples themselves, even though they're low dispersity, they actually do have a fair amount of dispersity within the domain. And now, using a much simpler and quicker procedure, Cheng and co were able to take a single polymerization, then purify it in about a day or so, and you can see that we get a fairly different phase morphology, phase diagram, that, in my opinion, is a much better representation of what the morphology is actually like for these diblock copolymers. You can see the very stable BCC phase, very stable sigma phase, the A15 phase, and then the hex phase. So again, really looking into new morphologies for these simple diblock copolymers. But can we actually even push it further? And this is some work that Ji Sui and Adam in Chris Bates's group and my group have done recently, pushing the range of different repeat units as well as the molecular weight. I'm not going to go into this in any great detail, but just to say that from the parent block copolymers, which are in many cases either disordered or very poorly defined cylinders, after fractionation, we do actually start to see this very rich morphology for the different samples. Our range of monomer units is also vastly increased. And more recently, what Cheng has been able to show is that this actually allows us to purify both homopolymers, diblock, triblock, and grafted systems of molecular weights 50,000 atomic mass units and above. So I apologize for the technical difficulties today, but hopefully I've given you one simple message that you'll remember, and that's this concept from Sir John Cornsforth about simplicity and enabling the development of user-friendly chemistry that is available to non-experts, and that is actually really healthy for the polymer chemistry community and really allows more people to join the polymer chemistry community. I'd like to acknowledge my group. I've had a wonderful, wonderful group of researchers over the years. This is one of our most recent photos. And of course, support. We've been supported by the National Science Foundation through their MERSEC program here at UCSB for many years. Dow Chemical has been a long-time supporter of the research. And I specifically spoke at the end about the work that Cheng has done. And Cheng was supported by a fellowship from the Australian government through their National Health and Medical Research Council. So I'd like to thank all of you for your attention this afternoon. Again, apologize for some technical difficulties. And I'd just like to really end by thanking the pioneers of ATRP, Chris and Mitsuo, for all of their inspiration, especially for me over the last 15 to 20 years. So with that, I'm happy to take any questions and thank Chris's group again for the invitation to speak to you this morning. Thank you, everyone.
Okay, thank you, Professor Booker, for your amazing talk. It was very interesting. So we have a few questions already in the Zoom, and maybe I can start by a question from Shinsuke Segawa, and they're asking, according to the TLC, the redder or the longer oligomers seem to stick to the base point. Is it normal behavior of the polymers? And he's saying, I assume the longer oligomers should be less polar and move more on TLC.
Yeah, so let me paraphrase the question, see if I understand it as well. TLC is a good indication, but what we've tended to find is that gives you an idea of how to begin the separation. But by using solvent gradients, you can certainly move things off the baseline. You can also, through solvent gradients, control which materials elute first. You can also use different column supports. You can do this via reverse phase as well as normal silica phase. And so there's a lot of variability and tunability in both choice of solvent as well as stationary phase.
Yeah, excellent. We have also a few questions about how do you compare this technique with preparative GPC for the separation of oligomers? Do you think prep GPC would be possible to efficiently fractionate the oligomers?
Yeah, so again, let me repeat and paraphrase the question. How does this compare with prep GPC? I think they're complementary techniques. I think it really depends on the system. Some systems may be easier to do by prep GPC. My students tend to like the biotage because I think the barrier to entry is much lower, and I would say this is potentially an easier system to use. But prep GPC certainly has a role to play, and I think these biotage separations also have a role to play. And it's somewhat system dependent, and I would probably try this procedure first, and if this procedure doesn't work, then maybe prep GPC. And potentially these two techniques combined may actually allow you to do some purifications that again, would be extremely difficult, if not impossible, using other techniques or the techniques alone.
Okay, excellent. So there's another question from Brooke Wersa, and she's saying, do you envision that these chromatographic separations could potentially be applied to nonlinear architectures or a mixture of linear and nonlinear polymers?
Yeah, and so I tried to touch that on at the end, and this is some work that we're doing, especially with Chris's group, and that's extending this to star polymers, grafted polymers. I'm really interested in gradient systems. Can we start to look at gradient systems and, separate different gradients from each other using this technique? So I'm quietly hopeful that we'll be able to prepare some really interesting libraries of gradient materials using this procedure. And again, getting back to one of my key messages, controlled radical polymerization, and especially ATRP, has really opened up this concept of gradient copolymers. And it's really nice to be able to then look at those materials in this way and then try and make libraries of these materials that, again, without ATRP and other controlled polymerizations would be difficult to make.
Okay, excellent. And one question is about, have you tried to stabilize the gyroid phase, and how easy do you think that would be?
So can you repeat? Let me repeat the question, see if I understood. Have we tried to stabilize the gyroid phase?
Yes.
Okay. We have not tried to stabilize the gyroid phase. We do see it in many of our libraries. If you mean stabilization, making an area or having a larger gyroid area, we tend to find that actually happens, and I think it's getting rid of homopolymers and also cleaning up the dispersity of the chains using this technique. We find that these complex phases like A15 sigma gyroid tend to become more stable and tend to increase in size. And so, that's a long-winded answer to your question. But again, I think that the purity of the die block libraries that we're examining is allowing us better access to these more complicated phases.
Okay, excellent. I think for the interest of time, we can stop questions. And thank you, Professor Hooker, again, for your amazing talk and also answering questions, and also the audience for asking questions. Maybe we can move on to our second presentation.
Fantastic. And I will try and fix my headset. There you go. Thank you, everyone.
Yeah, thank you. That would be perfect. And our second speaker is Professor Krzysztof Matyjaszewski. Chris is the J.C. Warner University Professor of Natural Sciences at Carnegie Mellon University, and is the Director of Center for Macromolecular Engineering and the CRP Consortium. He has been elected as a member of the National Academy of Sciences, Engineering, and Inventors, and is a fellow of the American Chemical Society and the ACS Poly and PMZ divisions. Chris has been awarded with many prestigious awards such as Benjamin Franklin Medal in Chemistry, the Dreyfus Prize in Chemical Sciences, Chemistry of Materials Award, Axel Nobel. But in particular, I would like to mention the recent award that he received from ACS this year, and is Paul Flory Polymer Educational Award, which I think truly reflects Chris's commitment and effort in educating people and training people in not only in related to science or research, but in general aspect of academic life and research. So as his students, we are extremely grateful for the opportunity to learn from him. So with that, I would like to turn over to Chris, and looking forward to listening to his presentation.
All right, good afternoon. First, thank you very much, Craig, for really delivering such an amazing lecture. Can I ask if my screen is visible and the pointer also works properly?
Yes, everything.
All right. And thank you, Sajat, for the introduction. What I would try to tell you today is really about ATRP and how we can make it more active rather than dormant. So we'll be talking first about some mechanistic aspects of ATRP, and then taking two examples of materials, something related to bioconjugates, conjugates with nucleic acids, with proteins, and also exosomes, and also the organic inorganic hybrids with certain nanoparticles and grafting from surfaces and arranging them sometimes in the form of lithium metal batteries. So ATRP is based on a free radical as active growing intermediates. And like in a conventional radical process, the frequency of monomer addition to a chain end is, roughly speaking, around 1 millisecond. And after 1,000 monomer additions, after 1,000 milliseconds or 1 second, there is a termination process. So during this time, 1 second of the activity of a chain, it's impossible to make these beautiful structures which Craig showed, block copolymers or potentially gradient and some others. So it was a challenge for many years, how you can extend life of propagating chain from seconds to hours or maybe even days. And we do that by equilibrating these active species with dormant species. So dormant species are typically alkyl halides, and then they are activated by transition metal activators to reform radicals, which can propagate maybe once or twice, and then are deactivated with this deactivator copper-2 species back to a dormant state. So during the last 20 some years, we developed catalysts which are now billion times more active than originally used. So because of that, we can reduce amount of copper catalyst to parts per million, but we have to face always radical termination. Every act of radical termination will convert irreversibly activators to deactivators, and reaction would stop. So we need to regenerate continuously these activators by some mild reducing agents, something like ascorbic acid or maybe sugar. It can be also externally controlled electrical current, light, or mechanical forces. I have to add that this ATRP catalytic system is rather special because it consists of two forms, activators and deactivators. Without activators, there would be no polymerization because only dormant species will exist. Without deactivators, there would be conventional radical polymerization because there would be nothing available to convert this active to a dormant state. And of course, controlling polymerization is first thing, but the second is how we can use this technique to these beautiful block copolymers, which Craig showed, or some more sophisticated structures, including bioconjugates, and sometimes also the organic, inorganic hybrids. So sometimes when people would say, what is a prerequisite? What is a most typical feature of a controlled radical polymerization, sometimes defined by IUPAC as reversible deactivation radical polymerization? And most people would say, you need to reduce concentration of growing radicals much more than in a conventional radical process to prevent radical termination. And this is not true, because there are some very fast controlled radical polymerizations which can be completed within sometimes minutes, and they are still well controlled. So really the main distinction between conventional and controlled process is that in a conventional process, nearly all chains, essentially 100%, except this tiny fraction of actually growing species, are terminated. And in a controlled process, we have maybe 1% or 2% of that chains, and 98% are either in a form of active or dormant species. So the second important feature for synthetic purpose, which Craig so nicely articulated, is that you can extend life of propagating chains from seconds to hours. And we do that by equilibration with various types of a dormant species. We can use, for example, stable free radical, nitroxide, something what Craig developed many years ago in form of a tipnol, or classical tempo derivatives. You can also use here organometallic species, and in that case, it would be cobalt-2 derivatives and formation of organocobalt derivatives, chemistry very similar to vitamin B12. Or we can do that with this dual catalytic system consisting of activators and deactivators in ATRP. Or you can apply also the degenerate transfer. In that case, radical can take this atom like iodine or potentially dithioester or some other group, and then itself become dormant and unblock the other one to be able to propagate. So the key feature for the control in all of these systems is how many times you propagate before you exchange, how many times you propagate before you deactivate, either in ATRP or these nitroxide mediated systems. If you add 1 to monomer units, you get polymers with very low dispersity. If you propagate 1,000 times, you get conventional radical polymerization. However, maybe the most important feature is also the initiation process. We can get in a controlled process quantitative initiation. In conventional radical process, we have steady state in which rate of initiation equals to rate of termination. And in order to propagate 1,000 times faster than terminate, in that case, initiation is also 1,000 times slower. So you cannot have well-defined structures. You cannot make star polymers, which would grow concurrently together. You cannot make block copolymers. In controlled processes, rate of propagation must be still 1,000 times faster than rate of termination, but rate of initiation is independently controlled and can be faster than rate of propagation, because steady state of radicals is defined by this activation-deactivation process. So generally, in all of these systems, you could think that you take this 1 second life of propagating chain, and then you divide it into 1,000 pieces, 1 millisecond each, and then insert within every millisecond activity, let's say 1 minute dormancy state. So now this 1 second is still 1,000 milliseconds plus 1,000 minutes, so essentially becomes equal to a day. So what is the typical scope of ATRP and some other controlled radical polymerizations? We can make, as Craig showed, oligomers. Degrees of polymerization can be sometimes 2 or 3 or 4 or 5, and typically we can reach molar masses even exceeding 1 million, with the dispersities, as Craig said, 1.2, sometimes 1.1, or sometimes less. So very high uniformity of these chains. In ATRP, we need monomers, which would typically stabilize radical by either a triple bond or double bond, like methacrylates or acrylates or acrylamides, or also you can have a benzylic structures. Initiators, very often, they mimic the structure of growing species, and tertiary structure like isobutyrates are more active than secondary propionate or primary acetates. Radical stabilizing group, cyano would be better, and phenyl and esters pretty similar. The range of halogens is done in a way depending on the stability or bond dissociation energy between not only carbon and halogen, but also copper and halogen. Therefore, bromide are more active than chloride and more active than iodide, which are normally much stronger bound or much weaker bound to carbon atoms. And concerning ligands, I can show you on the next slide that during these 20 years, as I mentioned before, we developed catalysts which are really now 1 billion times more active than originally used. There is a beautiful correlation between activity and redox potentials. This is a really many years of work in collaboration with Professor Gennaro and Abdiris Akise in Padova, but now we can make catalysts which are really literally 1 billion times more active than before. Because of that, we can have a lower concentration of copper, extend range of monomers, work under milder conditions, and in fact, not only working with copper, we can work also with iron. We can do reactions in the water, in homogeneous or dispersed media. Even sub-ambient temperatures are possible. Some will be oxygen tolerant, as I will show you today later, and prepare various copolymers and hybrids. So let me go now to the essence of ATRP. So atom transfer can happen in a couple different ways. So here you could see that this preferred process is inner sphere electron transfer, where bromine will bridge carbon with copper and form radicals and oxidize copper to species. This is one possibility. There is also a possibility that you can have outer sphere electron transfer, formation of a radical anion, which would then dissociate to radical and anion. Or you can have a concerted process, dissociative electron transfer via a so-called sticky electron transfer process. And finally, you can have also oxidative addition passing through the copper-free intermediates. So we calculated together with Michel Cout and Peng Liu transition states for these three reactions. You could see that the lowest transition state energy is this inner sphere electron transfer process. One with this dissociative electron transfer has 14 kilocalories per mole higher activation energy. This corresponds to reaction rate, which is approximately 10 to the power 14 times slower. So if this reaction would have a half-life time 1 second, this one will have a 3,000 years. And this one will have a maybe not 1, but 15 billion years. So this is from the time of a Big Bang, essentially, because activation energy is now 30 kilocalories per mole higher. So how does the reaction occur? So in some sense, we start with this copper-1 species. It is 3D9 configuration, so it is a closed shell singlet. And then the product is a doublet with 3D9 configuration, but you pass through transition state. And this transition state is very unusual. It is not straight, not 180 degrees, but carbon-halogen copper bond is bent, and this is around 140 degrees. This is due to some attractive interactions between substituents and ligands on copper. Transition state is rather late. It means that it resembles the products. So you could see that in a transition state where you have the highest energy here, the charge is practically developed already like in a product. The same situation is with a spin. So transition state is rather late under these conditions. So there are two components to atom transfer. One is alkyl halide, the other one is a copper complex. So alkyl halides, which are shown here, they have a difference in reactivity by factor of 100,000. In fact, we have some alkyl halide initiators which would be additional 40,000 times more active. So tremendous difference. And in fact, you could think that the bond dissociation energy between carbon and halogen would be most important. In fact, it is important, but not only. So here is a dependence of the activation energy for bromides and for chlorides. And you could see that bond dissociation energy will be different, but approximately 10 kilocalories per mole, which means that bromides should be 1 million times more active than chlorides. In reality, they are maybe 10 or 20 times more active. The reason is halogenophilicity. But as much as carbon prefers chlorine, as much copper prefers chlorines. So therefore, it is both contribution of a bond strength and halogenophilicity. As a result, bromide are more active than chloride, but iodides, which have a very weak carbon-iodine bond, have also extremely weak copper-iodine bond. In fact, copper-2 iodides are not known compounds. So here you have two parameters which are very important. If you move now to the catalyst, there are really three parameters which are very important. One would be electronic effect, which can be defined by energy of a HOMO level energy. And the other one is a steric effect. The alkyl halide must come inside this cavity of a ligand, so it can be really defined by a % of buried volume. But equally important for kinetics is flexibility of the ligand. It must go from copper-1 to copper-2 process, and in that case, sometimes can go from tetrahedral to trigonal bipyramidal structure. So ligands which are tetradentate, like TPMA or TREN, they are really preferred because you have a very little reorganization during this process. So let me come back to these processes which are run now not with 1,000 parts per million of copper, but 10 or 20 ppm of copper. So this is a big improvement. And in fact, it allows to work now with a very low concentration of copper, but we cannot prevent radical termination. Any act of radical termination will oxidize irreversibly copper 1 to copper 2, and reaction would essentially stop. So we need to regenerate these species. There are many advantages of this low ppm copper system because copper 2 is oxidatively stable and we can tolerate oxygen in some sense. And one interesting feature is that, in fact, if you stop regenerating this process, you can stop entire ATRP. So no Tromsdorf effect or runaway reactions. So what kind of a reducing agent we can use here? It can be chemical species like ascorbic acid or tin octate. It can be radical initiator as simple as AIBN. Can be piece of iron wire or sometimes sulfides. You can have external field like electrical current. You can have also ultrasound or mechanical forces, and you can have also light. And this is something which Greg referred to. It's a project which was run by Greg group, Atina Anastasaki, but also Sajat, who is chairing this session. And we observed that sometimes when you switch light off, reaction can stop nearly instantaneously, but in some cases can continue for much longer time. So this is a little bit special process because in this photo ATRP, everything is based on photo reduction. So we reduce copper 2 to copper 1 by light in the presence of some electron donors. And if you have a large enough copper 1 accumulated, in that case, this termination process cannot stop the reaction and it can continue for a longer time. So it depends essentially how much copper 1 you have in this system, or what is the total amount of copper if you wish. So for example, in this graph, you could see if you use more and more copper and more ligand, reaction is faster, and also this stopping is not as fast as it could be. In addition, you may have effect of solvents, and you may have also effect of the ligand or complex itself. So here is a really very fast switching, 20 minutes on and off, and you could see that for hexamethylated tren, the most active ligand, the reaction stops pretty fast in a dark period. For TPMA, it doesn't unless you go to a longer off time, and in that case, you could see that the reaction eventually stops. If you would go to PM-deta, practically there is no stopping of this reaction. You would need to wait probably more than 20 hours to stop it. So this is related to the amount of copper 1 and the equilibrium condition. Here is less than 1% or 99% of copper 2. Here would be 10% of copper 1, and here would be 13 or 15% of copper 1. So how can we stop this system with PM-deta? Can we just wait for many hours, or can we do something to stop it in the dark? In fact, the easiest way is to expose it to oxygen. After opening to air, the reaction stops nearly completely because all of this copper 1 gets oxidized to copper 2. And then you can regenerate it if you wish. So we modeled these reactions, and we found that if we would like to model this dark period with a conventional radical termination, reaction should continue much more than it does. So in fact, not only conventional radical termination, but so-called catalyzed radical termination matters. These copper 1 species are very often extremely active. They can react not only with alkyl halide, but also with radicals, forming the organometallic copper 2 species. These are paramagnetic, so they act like radicals, and they can react with another radical and favor fast termination process. So this is what happens with this catalyzed radical termination process. Now, another possibility, instead of oxygen, we could use some other oxidizing agent. like ferrocenium cations. So again, ascorbic acid promotes polymerization, then ferrocenium ion stops, and then we can add more ascorbic acid and reaction continues. Or you could do the same ascorbic acid and air. Ascorbic acid and then stop. You can put more ascorbic acid, it starts. Oxygen stops. And in fact, all of these polymerizations are well controlled because you do not kill chains, but rather you kill the catalysts or activators, if you wish. So this is an interesting possibility. What happens with oxygen as such? There was a beautiful review by Cyril Boyer approximately 2 years ago when he analyzed many papers with oxygen tolerance. So some of them, probably majority, is with different types of ATRP systems. And very interesting and intriguing is a PET raft, which is both energy and electron transfer reactions. You may have also something related to enzyme degassing, as we discuss in a moment. And sometimes you can have even polymerization through oxygen. So oxygen reacts with the organic radicals, form peroxy radicals. And these peroxy radicals are rather stable, but still can react with the monomer and get incorporated. You eventually can produce polyperoxide, which may be a little bit challenging in handling, of course. In the case of a copper, oxygen can also oxidize copper 1 to copper 2 species and reaction would stop. You may also take benefit of this reaction. This is last year paper showing on the oxygen reduction reaction with exactly the same copper TPMA system. So there is the oxidation of copper 1, formation of this peroxy species in the presence of protons. Eventually you can produce hydrogen peroxide under these conditions. So this is a really interesting possibility, but how can we degas the system in the easiest way? So first example was reported by Professor Yusuf Yakci from Istanbul University for conventional radical polymerization. He used glucose oxidase and ran the reactions essentially in a system open to air. Then later it was adopted by Bob Chapman for enzymatic raft process. So here the glucose and glucose oxidase could consume oxygen from hydrogen peroxide, which is typically very poor initiator under conventional radical conditions. In ATRP, it's a little bit different, as you will see in a moment, but we tried to do exactly the same process. We reduce copper 2 to copper 1 in the presence of a conventional radical initiator, low temperature, D44. And then we use glucose and glucose oxidase and consume oxygen, forming this gluconic acid or lactone and hydrogen peroxide. And hydrogen peroxide then unfortunately participated in this Fenton-like reaction, oxidizing copper 1 to copper 2 and forming hydroxy radicals, which produce new chains. So here polymerization worked very nicely, but you could see that molar masses, instead of these predicted values, get molar masses significantly smaller. Instead of reaching, let's say, 400,000, they reach 50,000 only. So this is a problem. How we can avoid formation of these new chains, because if you want to make a conjugate block copolymers, as Craig said, or star polymers, or any other materials grafting from surfaces, we should avoid these spontaneously formed chains. So we're thinking about it, and Alan and Lia, they came with idea borrowed from biochemistry, from Krebs' respiration cycle, that one can use pyruvate. Sodium pyruvate will react with hydrogen peroxide very, very fast, faster than the copper species, and produce inert carbon dioxide, water, and corresponding acetate anions. So more or less, it is a very simple process. It's a non-toxic, safe system, highly efficient for hydrogen peroxide scavenging. And this breeding cycle essentially is based on this oxygen diffusing in and carbon dioxide getting out. it is like classical breeding process. And now you could see that molar masses predicted and molar masses measured are in a very good agreement, and we do not generate new chains. However, there is a challenge. There is still glucose oxidase in a reaction mixture. Can we somehow remove it or get rid of it? And this was a motivation of the work which Greg Szczepaniak did, using the same pyruvate, but without glucose oxidase and without glucose at all. This is based on the fact that the copper pyruvate species are light sensitive and they can decompose from the same carbon dioxide like in a breeding process. And the process relies on the fact that the copper-2 bromide species in water, they are dissociating from the naked copper-2 species. And now we have a pyruvate anions, like previously we demonstrated for carbonate anions or bicarbonate anions. They would bind to copper, and then this bond can be broken under irradiation and reduce copper-2 to copper-1, start the reaction, but also form these pyruvate radicals, which are very unstable. They decarboxylate and form these acetyl radicals, which can be scavenged one or the other way. So you could see here that it takes, for the system completely open to air, approximately 15 minutes, and then polymerization starts. And you could see whether it is capped vial or open vial, within 30 minutes, you get 97 or 99% conversion, low dispersity, good control of molar masses and dispersities. So this is a very good system for water, but sodium pyruvate is very poorly soluble in organic solvents. So can we run the reaction in, let's say, DMSO or DMF? And this can be done in the presence of the phase transfer catalyst. So we are using here tetrabutylammonium bromide, which exchanges cations and forms this organic soluble pyruvate with tetrabutylammonium bromide. And sodium bromide, which is formed in situ, can be easily filtered, and then you can get polymers, again, in a short time, good control of molar masses and low dispersities. So how this system works, it's a little bit complicated structure, but we have to realize that copper-1 can react with oxygen and form, like in this oxygen reduction process, eventually hydrogen peroxide. Then sodium pyruvate will convert hydrogen peroxide to CO2 and acetate anion, but also second part of the sodium pyruvate reaction is based on this exchange between bromide, formation of the light sensitive pyruvate copper-2 species, which then can be reduced to copper-1 by radiation and formation of these acetyl radicals. So here it is shown again that you have a sodium pyruvate in the presence of copper-2, you generate the corresponding copper pyruvate 2 species, which then after irradiation produce copper-1 and this acetyl radical. Acetyl radical can also take bromide from the copper-2 species, reduce it to copper-1, and form the acyl bromides, which in the aqueous system, they are very hydrolytically unstable and generate acetate anions, or can small amount of them initiate polymerization. So we cannot go to molar masses in this system in a range of 1 million or so, because there would be small amount of new chains from these acetyl radicals. We are now working how we can potentially improve selectivity in this reaction. Alan and Leah, they also look at the system which is really relying on oxygen. So it needs air to start polymerization. So this is an enzymatic cascade starting from this glucose oxidase process and hydrogen peroxide. But now we can eliminate this V44 radical initiator by using second enzyme, horseradish peroxidase, which in the presence of acetyl-acetone produces ACAC radicals, which can reduce copper-2 to copper-1 in situ and start the reaction. So this has been really done for several different monomers. This enzymatic cascade, glucose oxidase, horseradish peroxidase, acetylacetone, and polymerization in situ. You could see without oxygen, nothing happens because there is no source of radicals. Then you open it to air, polymerization starts. You close it, slows down, starts, slows down, starts, slows down, and molar mass is very nicely increased to higher molecular weight. You could see here the example of using these two enzymes, enzymatic cascade, to grow polymer chains from enzymes or proteins. We take here BHS or BSA, and in that case, by using corresponding NHS activated species, we can put ATRP initiator, around 30 of them, and then grow polymer chains and eventually digest this enzyme, analyze molecular weight, and check how good control of molecular weight and dispersity it is. The same story can be done and has been done with nucleic acids. In that case, we have a macroinitiator, DNA, these two enzymes, and then we grow polymer chains in a progressively controlled way. So these systems can be applied to various modifications of nucleic acids, but also proteins and enzymes. This is a work which we do together with Alan Russell and also with Professor Das. We can now make enzymes which can work in organic solvents by putting these nano-armored structures. We can decorate some proteins with polymers, and then they can be taken orally for therapeutic purpose, having a responsive system, thermostable, conductive, immunoisolating, and some others. But I would like to spend now a few slides on the exosomes. This is a work which is done in collaboration with Professor Das, and all of that is done by Sushil Dadwal and also Sai from group of Professor Campbell. So what are exosomes? Exosomes are one type, probably the smallest, of vesicles of a size of approximately less than 100 nanometers. They serve as intercellular messengers, and they are present essentially in all body fluids, in saliva, in tears, in when we swear. And in fact, if you kiss, you exchange exosomes with your partner. So be careful, especially during the time of the COVID-19. They can be very easily internalized inside cells, and they can even cross blood-brain barrier properties. They are very rich materials because they take from the cells many different species, including nucleic acids and microRNA. They take enzymes, they take various types of proteins, and some of these proteins, like integrins or these tetraspanings, they would be sitting on a periphery of these enzymes. And even you can have some proteins for membrane trafficking and lipid rafts. It is not raft for raft polymerization, they are just pieces of lipids there. So for biologists, in some sense, it's an issue of the, both of them can carry disease, but they can be used for curing process. The problem is very short lifetime. They typically survive a couple minutes, maybe up to several hours. And the question is how we can stabilize them, and can they, after stabilization, still deliver the corresponding function? So we are thinking about process, which is based on the functionalization, something similar to what Professor Hocker did by attaching polymers to living cells. And here we use exosomes, and there is a part of the cholesterol and DNA. After vortexing for 5 minutes, we can put maybe 10,000 of these cholesterol DNA constructs, which can be either now coupled with the polymers by a process of grafting onto, or can be connected with the ATRP initiator and start polymerization by grafting from process. It's a question how preserved functionality will be, how good blood circulation, and can we deliver a cargo here as well. So in one example, this is the grafting onto process. It's shown that you can put up to probably maybe nearly 10,000 of the corresponding polymers, and density of grafting is approximately around 1 chain per maybe 8-10 nanometer squares. Analysis by field flow fractionation shows that just before grafting, these exosomes are very uniform vesicles, like hard spheres. Judging from the radius of gyration to hydrodynamic radius, then they will become hairy particles and eventually vesicles with many antennae and densely grafted segments. The charge also after grafting of polymer really disappears because DNA carries very strong negative charge. Now, if you go to a grafting from process, it's very interesting because you can make a block of polymers, you can make chain extension. This is done under very mild conditions. This is with glucose oxidase with a blue light process. It can be done either way. And you can make block of polymers, in fact, with a cationic process. You cannot do this cationic process by grafting onto because they would interfere with the membrane and with the DNA as such. So this is access to cationic polymers this way. The stability is much stronger after grafting. This is what happens with the native exosomes. After 30 days, they aggregate, and these exosomes with polymers, they stay intact at lower or higher temperature as well. Now, you can attach polymers, but you can also remove polymers. And this is done by using this nitrophenol linker. And in that case, after the degradation, you can remove completely polymer chains. So here's an example of the showing case of native exosomes when exposed to the enzyme, to trypsins. If they are exposed to trypsin, practically nothing happens. Without trypsin, you could see exosomes and some shaded proteins. The same will be for the case of the polymeric modified structures. However, if you read it with light, you could see that these exosomes constructs, they disappear, and then you have a surface protein, so you can attach polymers and remove them very efficiently. So they are stabilized and circulate in blood much stronger. So you could see here what happens with the native exosomes and these 3 different types of polymers with either PO side chains or with this zwitterionic structure or with these DMSO-like structures. Interestingly, if you look at the biodistributions, whether they are native or with 3 different types of polymers, biodistribution doesn't change. So in that case, they can be delivered exactly in the same accuracy. So with that, I would like to switch to organic inorganic hybrids in a remaining maybe 5 or 10 minutes. And this is a work which we carried together with Professor Boxstaller and Jay Whitaker and also Carmel Majidi. And we try to graft polymers in a well-defined structures by using substrates which are flat wafers, spherical nanoparticles, cylinders inside or outside, and making them, as Craig was showing, very uniform. How we can control these structures that they practically become now the systems with like plastic photonic crystals, which can be stretched, can be processed, can be carried out in a different way. So this is a work done by Zhongyu Wang, and he tried to check how the grafting density on nanoparticles, starting with a very dense system with a grafting density around nearly 1 chain per square nanometer, going down to a very loose or sparse grafting, approximately 0.05 chain per nanometer, and then having this intermediate part, how they would change with the degree of polymerization of PMMA or polystyrene. So you could see that going to a less and less dense grafting, you start observing special organization of these nanoparticles. So these are pretty isotropic systems. And here you could see that you have something like a really strings of these nanoparticles separated by the polystyrene chains. So you have two different types of spacing. Intrastring, maybe 1 or 4 nanometers, and interstring around 20 nanometers. This is even better shown on this cartoon. So these are isotropic system, and this here you could see that there is an attraction between these nanoparticles, and polymer chains are expelled, and they form these connected string-like structures. These can be extended to block copolymers. So block copolymers, we can start with a silica with PMMA, and then they can be extended with the corresponding polystyrene, either short or longer ones. And again, morphology would be pretty different depending on the structure. We can have a more polystyrene and dense PMMA grafting, or sparse PMMA and even more sparse polystyrene. So you have some unreacted even PMMA nanoparticles. So this gives you a very intriguing system. This is a possibility of having this type of a strings or train, if you wish. And depending now on a graft density, if you have a very low, in that case, you will have even some nanoparticles not grafted. They would be sticking inside these PS grafted systems. You can do the same by simply mixing these ones with the naked PMMA, and they would be loaded inside. In that case, so these structures loaded with these structures will give you this type of a cluster. So I wanted to show you two more short stories. So one is about grafting from the liquid metals. So typically we know liquid metals which are based on mercury, but this is very toxic and not recommended material. But liquid metals have a very special applications in soft robotics because of the thermal conductivity, because of the also electrical conductivity and elastic properties. So one of these examples is eutectic gallium-indium alloy, which has a melting temperature around 15 degrees. So at room temperature, it is a liquid. And then you can disperse it by ultrasound in a solvent and use this BIBADA initiator with carboxylate group, which can anchor to the surface. And then you have the corresponding bromoamide to grow, for example, polymethyl methacrylate or polybutyl methacrylate, which will become very elastic material. You can very easily disperse it, and then adding 1 drop of HCl, you separate this again, and the size of particles in a dispersed state is in a range of approximately 100 nanometers. They are so small that they become transparent, in contrast to material which is now built on a macroscopic structure. I mentioned that they are elastic, very important for this soft robotics, and very intriguing possibility is change or extending the range of a use of temperature, because again normally crystallizes around plus 15 degrees. In this nanostructured state, you can cool it down to minus 80 degrees, and then only it starts crystallizing. And then it melts at around minus 25 degrees. So you can extend tremendously useful range of application of these again nanomaterials. You can make them by grafting from, but you can make them also by grafting onto. This is an example of a block copolymer, something similar what Craig was showing, based on the T-butyl acrylate. After hydrolysis, we get acrylic acid, which can attach to the surface, and then they can be dispersed and stable even after 30 days. They can be separated, redispersed again, And depending now on a centrifugation, you can also fractionate their size and have it in a different way. So the last 3 slides are related to the lithium metal batteries. It's a work which we do together with Professor Whitaker, and it was started by Sipei Li, who is now postdoc at MIT. So we expect that in maybe 20 years, more than half of all passenger cars will be based on lithium batteries. Currently, we are using lithium-ion batteries, and we would like to extend useful range of cars from not 100 miles, but 500 or maybe 500 to more than 1,000 miles on one charge. So in that case, we need to make higher energy density materials. So if you compare classical anode, which is based on graphite, with lithium metal, you can gain 10 times with the theoretical capacity. But the problem with lithium metal anodes is that during charging discharging process, they start forming in an uncontrolled way dendrites. These dendrites grow longer and longer, and eventually they can touch the cathode and make a short circuit, and the battery would fail and sometimes may have a catastrophic even consequence. So the problem is that you can use for protection solid electrolyte, but if you are using conventional lithium metal, lithium foil, there would be a lot of the empty space, and this is the way how these dendrites starts growing. So can we use semi-liquid metal anode? And in that case, this interfacial contact would be much better. We did that by using just lithium foil at higher temperature with mono-methylated and monohydroxy pegylated structures, and then adding a little bit of a carbon black for better conductivity, we developed this flowable lithium anode. It has a very good properties. You could see stable cycling over 400 hours, and you have these cycling back and forth systems. The size of the particles during the cycling process slightly increases from 27 to 34, more or less, after stripping 60% of lithium. And we are using here the solid electrolyte based on the lithium, lanthanum, zirconium, and tantalum, so LZTO. Another approach on a last slide is really shown that you can have these solid electrolytes with a very good properties. This is yttrium stabilized zirconia, nanoparticles. They can be either blended with a polymer or can be grafted with a polymer. And there is a dramatic difference if you start grafting because you have a very uniform distribution and the dendrites are strongly suppressed. So you could see here on this graph, using 3 milliampere per square centimeter, this is what happens with a bare lithium. There is essentially short circuit very quickly. This is what happens with a blend of the same composition. And this is what happens with these grafted particles with the same composition. And this is done after thousands of hours of a cycling process. So we work in this project with a collaboration with Ionic Materials. And I wanted to show you how different these lithium batteries can be with inorganic solid materials. You can puncture them, you can cut them, and there is no flammable system. You can put them together and essentially connect to the iPad and restart it again. So I think that this is a really huge possibility, not only for batteries, but potentially this flowable system for the larger grid scale energy, and hopefully the polymer chemistry can contribute here very significantly. So with that, I would like to really summarize that ATRP, in fact, is much more active than dormant, although we need always these dormant species in order to equilibrate and extend life of growing chains from seconds to hours. We develop new catalysts, which are very powerful. They can be used at very low concentrations, and you can use various reducing agents to regenerate and also stop at any time you want to stop them. This leads to formation of polymers with controlled compositions, something like gradient, which Craig mentioned before, various controlled topologies like stars or even cyclic polymers or corresponding networks, various functional polymers, more complex architecture, eventually for various applications, even for the bio-related systems, for energy-related systems, for some advanced materials. So I would like to thank my group members doing many creative contributions. And I circle here this group of 6 who organize by themselves this series of seminars, Sajat, Francesca, Greg, Sushil, Mike, and Julia, but there were many contributions from the entire group as well. And because of a different time, we are allowed, in fact, to return to labs now, but still our meetings are via Zoom. So this is the current image of the all group members, which I appreciate their contributions and passion for doing research and collaborative spirit very much. So thank you very much, Sajat. I am ready to answer some questions.
All right, thank you so much, Chris, for your excellent talk and all aspects of ATRP. We have 2 questions about general considerations for doing ATRP. One is that what ATRP technique would you recommend for making, say, polystyrene or polybutyl acrylate that would be easy to purify?
Yes, I think that probably the easiest way is to think about lower concentration of copper, but it's a question what kind of impurities you think about. Ideally, you could think of having 5-10 ppm copper system using a photo system, maybe even ATRP. If you're afraid of having metal residue, then you can go to the organo ATRP using photoredox catalyst. Of course, they would be still left there. It's a question how to remove this type of the photocatalyst. So it's a question how to remove it. And for example, going to EATRP, we can, by the electroreduction process, we can recover 99% of copper, maybe 98% of copper by electrode deposition on the electrode. And then you can strip it back and recover. So there are several possibilities. To expand maybe on a styrene versus acrylate, acrylates are generally, and acrylamides, much easier to be controlled because they are inherently propagate much faster. And the issue in all controlled radical polymerizations is the ratio of the propagation to termination process. Termination is generally very similar for many systems, but propagation for acrylates and acrylamides are 30 times faster than styrene or methyl methacrylate. So a ratio which is defined Kp over square root from Kt would be like 1,000 times. So they are much easier to be controlled and much less contaminated.
Excellent. And the second question was about the choose of initiator. Why do you think we don't use just one initiator, such as EBIB, for any polymerization? What should we consider about choosing a particular initiator?
Yeah, bromoisobutyrate, EBIB, is a pretty efficient initiator for acrylates or acrylamides. But in fact, it is very bad initiator even for methyl methacrylate. So activity of EBIB is approximately 15 times lower than going chain of the methyl methacrylate. So under these conditions, if you want to make a short oligomers like Greg was showing, it would be very inefficient because you would have a slow initiation and faster propagation. So in that case, for MMA, you could use bromophenylacetate, which would be much more active. If you use EBIB for acrylonitrile, it is even worse. So sometimes you can think about a rule that your initiator should have a higher equilibrium constant and, in fact, product of the addition of a radical than the propagating species. So this is probably a general rule. At the same time, if you have a very active initiator, sometimes you can produce so many radicals at the beginning that they will kill one another. And in that case, there would be lower initiation efficiency. Of course, you can still use the same initiator, but maybe feed it or slowly add to the system. Or you can have an initiator and feed the catalyst, or maybe feed reducing agent. So it will be without this explosive generation of radicals at the very beginning.
Perfect. Maybe we can have two final questions. Andrew Friedman from YouTube is thanking you for the excellent talk and is asking, what is it about PM data that makes it so much less effective than TPMA or methylsixtrin at slow or stopping the reaction in the light mediated ATRP?
Yes, so maybe I can even refer to the slide which is taken from work which is just published in the last issue of Macromolecules. And really, the point is that in a case of PM data, you have equilibrium constant, which is, maybe I can enlarge it, by factor of probably 100 times smaller than in a case of a hexamethylated trend. This is 6 10 to minus 5. This is 4 10 to minus 7. Because you have a 100 times lower equilibrium constant, in that case, the ratio of copper-1 to copper-2 species is dramatically different. So in a case of this PM data, you could see that here you have 13% of copper-1 left, and in a case of hexamethylated trend, only 1% of copper-1. So it's enough to kill this 1% of the activators, reaction would stop. In a case of PM data, it can continue unless you will reduce copper-1 or oxidize copper-1 to copper-2. So this is really what happens if you expose it to air.
Okay, excellent. The last question is about polymer exosome hybrid. And do you think by changing the polymers or any other approach, this bioconjugation can control exosome deliveries?
Yes, so there is a possibility of further functionalization of the polymer chains with some, for example, aptamers, which may have a particularly targeted cells. At this stage, we did not observe any difference in biodistribution between native exosomes and the others, but by modification of polymers, you can have some targeted structures as well. So at this stage, we were looking at 3 different types of polymers, 2 neutral. One was polyethylene oxide methacrylate. The other one was this DMSO-based acrylate. And the third one was twitterionic. So all of them performed pretty well in a sense of the toxicity, in a sense of the stability. But I think that the next step would be to further address the chain ends of these polymers and functionalize them with some targeting devices like aptamers, for example, eventually antibodies.
Okay, perfect. Thank you so much, Chris, for answering all the questions. We can probably move to the final session, and I can see that Professor Hawker is also connected. and hopefully we can hear him as well.
Yes, I am. I'm back in the real world.
Oh, that's perfect. So, we were interested to also use this opportunity to learn about your adventures in academia and also your opinion as to what would be the future of the field. So generally, in our group, when we finish the project, we kind of ask this question: what is next? So I think we had also some questions like from Austin Evans, who was saying that given the emergence and maturation of all these techniques, what excites you more about future of polymer science? Or if I may add, how do you think the field should or will evolve in future to meet the demands from industry or also in academia?
So I can answer that by simply telling you what originally drew me to polymer science. So I'm a classically trained organic chemist. My thesis was on the biosynthesis of vitamin B12. And that was fun, but I wanted to find work that was kind of a little bit more applied, but still fundamental. And by chance, I stumbled into polymer chemistry. I did a postdoc with Jean Frichet at Cornell many years ago. And then I left for industry. I worked at IBM for 14 years before coming down here to UCSB. So what really attracted me to polymer chemistry was the broadness of the field, as I tried to illustrate during my talk, the ability to collaborate with people outside your comfort zone. And yet, by developing new synthetic techniques, you can actually make better materials that they, in turn, can use in their fundamental studies outside polymer science, in biomedicine, in microelectronics. So I still see polymer science as having that key enabling central position. And I think it's only getting stronger as we proceed into the future. There are a number of issues from an environmental viewpoint that I think that polymer science and polymer chemistry can solve. If we just look at COVID-19, there are a number of areas where biomaterials, as Chris pointed out, bioconjugated materials may play major roles in the development of vaccines, even something as mundane as bottles for vaccine. You know, you can use polymer science to make sterile bottles really much more efficiently than glass bottles. And so just so many applications and so many things from a societal viewpoint.
Yeah, if I may add to that, I fully agree what Craig said, and I can echo essentially his message, that probably the most interesting things happen at the interfaces, at the crossing different disciplines. And I think, as Craig was showing today, and I try to show, that we are between sometimes the science of bioconjugation or biomedicine, or sometimes battery field and some others. And this is really what happens, is most interesting. It's a question how polymer science can help to solve these problems, how we can do it in a more efficient way, because some of these fields are very barely touched upon yet. So in my opinion, for students, essentially the message should be that you should be as broad as possible, but you should be also extremely deep, the best in a field what you work in. You should be better than your advisor. You should be better than essentially anybody else in the world, because it's your work. At the same time, you should be very strongly connected to different areas. whether it will be bio or will be advanced materials or environment or anything else. So you should have a good grasp of these fields, because maybe in 5 years, your field will disappear. Maybe something else will be more important. So you have to be ready to quickly and efficiently switch from one to another field.
And if I can just add one point to Chris's, and Chris has pointed out this a number of times, collaborations, but also how the polymer chemistry community, I think, is really welcoming. And as we also struggle with diversity and diversity issues, I really do believe that one of the power of polymer chemistry, and especially for the future of polymer chemistry, is how welcoming the community is to as diverse a range of students, researchers as we can. And I'm always, pleasantly surprised, but recognize that we can do better. Whenever I go give talks at universities and visit other groups, that there is diversity within those groups, and everyone recognizes that we can do better with respect to diversity. So I think polymer chemistry is really, and polymer science is really primed to, be leaders in all of these areas that Chris and I have talked about.
Yeah, excellent. Thank you for that. And I think, yeah, as a student, I have always experienced this welcoming environment, but I think it's always, we all need to have this discussion about making it more, even better environment in terms of being inclusive, diverse, but also making it a cool place for everyone. And maybe one other point was that, what do you think about using ATRP, or I would add other control polymerizations in industrial scales? How big could we go, or what do you think is the biggest challenge in making these techniques usable in industrial scales?
Let me defer to Chris. He can answer that first, and then I have my own thoughts and opinions.
Yeah, I think that for many years we have bigger expectations than reality now. So I remember that years ago, Bob Madsen from DuPont expected that it would be a market of $20 billion a year of products made by controlled radical polymerizations. And it did not happen for maybe a couple of reasons. One is that probably industry did not feel enough sufficient need to make these much better defined materials. They tried by blending or mixing things, get something a little bit better, but without investing in the new equipment or potentially new materials. I think examples of what Craig was showing today, how different is a mixture with average DP6 versus 5 plus 12. It is a very good example showing that there is a lot of possibilities in these areas. I think some companies which started using ATRP, like Kaneka, they made some materials with unique properties, sometimes super soft or special sealants, energy absorbent, and so on. And still they are doing that on a scale maybe 1,000 kilos per shift, or maybe 3 times a day, rather than 10 times more. Of course, price would be 10 times lower. We discussed with several companies, and I think they are eager to do something, but it is still not yet at the level of expectations. And we hope that this may change, whether it is ATRP or RAFT or nitroxide mediated system. So not yet there. I think sometimes you need to talk to people from industry rather than from academia. And from academia, we are ready to help to develop anything possible, but people in industry, they are a bit reluctant. And now with the COVID, it may be maybe not better, unless you would go to the areas related more towards biomedical or maybe cosmetic systems. And I think this is area where Craig can comment as a really expert.
Yeah, so building on Chris's point, I also think that, you know, it's just a matter of time. Expectations sometimes for product displacement do not happen as quickly as people believe. Just because industry has invested in plants, they've invested in processes, they're not willing to change as quickly as maybe dictated by the performance increase. But it is happening. It is happening in high value applications first, where you're not talking about large volumes, but you're talking about selling materials for significant amount of money per pound, etc. And as Chris points out, that's biopharmaceuticals, that's personal care industry, microelectronics. So it's catching up. It's slower, but it is a constant improvement in the number of materials that are produced commercially, and it will steadily increase with time.
Okay, excellent points. And maybe as a final point, we have a comment from Jordan, who is saying, as someone who is getting ready to start graduate school in the coming weeks, is there any advice that both of you can offer to the next generation of polymer scientists? And I think this is true for everyone who has already started their graduate school or research or want to pursue their career in academia. So we will greatly appreciate your opinion about this point.
Yeah, and so this is a topic I feel quite passionate about. And the best piece of advice that I can give is to develop your professional network. Take the ability and time to introduce yourself to as wide a range of people as possible. Take advantage, even in the time of COVID-19, to get and develop your outside connections. Again, if I look at my own career, it really has been defined by my mentors, not just my immediate mentors, but mentors such as Chris. Chris has mentored me, even though he may not have realized it, many times over the years. And developing your professional network sets the stage for success, not only in academia, but also in industry, and from my own recent experience in entrepreneurial activities. I have benefited enormously from contacts that I made 5, 10, 15 years ago that, you know, because you have even the slightest connection, that's enough to get your foot in the door, and then things can go on from that. So my biggest message, if you're entering graduate school, is don't forget about putting a lot of effort into developing your professional network and take advantage of activities. In the near future, I hope that we will get back to in-face and in-person meetings. And again, just introducing yourself around, taking advantage of opportunities that maybe you are a little dubious about, but take it from me, every time I felt a little dubious about taking part in some type of professional development activity, every time I've finished and a week later said, boy, I'm glad I did that. So that's my big message.
Okay, so I probably could say that, you know, I love polymer science, so I would recommend to pursue this macromolecular chemistry, whatever it will be defined, you know, something large, whether it is long large in the different dimensions. But I mentioned before that it is important to be really very deep in something, but also very broad. So you need to take some courses which would be not necessarily in polymer science, but bridging to the material science, bridging to the biochemistry, bridging to the energy areas and some others. But probably most important to me would be to be passionate. That whatever you do, you have to have a passion. And you have to devote yourself to this passion. And in that case, it would give you a very good feedback, because every result will motivate you to go deeper, to do something more, and interact with people, like Craig said, and search for some new solutions. So I think that people who are successful are always very passionate and devoted to what they do.
Okay, perfect. Very, very interesting points. I think I should also mention Professor Hawker's recent article that he beautifully articulated his opinion on this on similar topics in Nature Review's Materials article titled "A Generosity of Spirit," I believe. So
yes.
It's always very inspirational and exciting to learn and to read that paper. So I would strongly encourage everyone to read or reread it. So that's very interesting.
And if I can just add one point, this is a great example. So I wrote this article, "The Generosity of Spirit," and I reached out to lots of my mentors and lots of the people that I have mentored to get their input. And so that's really, you know, an amalgamation of many people's viewpoints. And it was surprising how consistent the viewpoints were from person to person. And it didn't depend on their career stage as well.
Yeah, excellent. Thank you so much. I think we can stop here. We really appreciate your time and your efforts, sharing your research, and also all your valuable experience in academia. At the end, let me just share a few more slides about the webinars. I believe we should, okay. So we were extremely excited to have a wide range of people who kindly contributed to our webinars, making it as successful as it is. Professor Sommerling, Pion, Lutz, Kankulevich, Reinecke, Sykes, O'Reilly, Leipfart, Williams, and also Professor Hawker today. But also we had a range of postdocs and graduate students who contributed a lot to our webinars. Erin, who was started her group recently, Anthony, Suman, Kyle, Emily, Vivian, Bonnie, Austin, and Richard. So we appreciate all your contribution and kind presentations during this series. And finally, we would like to thank everyone for joining us and supporting us during this all past, I believe, 11 weeks that we started these webinars. It was a great motivation for us to receive your support and to continue this series. And hopefully we will be able to continue this in one way or another format in the future. And I should like to stop here and thank you all for joining us and all your support that you provided to us. Thank you, and I hope you all have a great day. Thank you so much.
Good. Thank you, everyone. Please take care.
So,
bye.
Yeah, thank you,
Craig.
Thank you, Chris. Take care, my friend.
Craig, if you don't mind, we will join a breakout room.
Oh, okay.